provide a papers associated report.
Dear students, Assalamu alaikum. I welcome you to the 14th program on Software Engineering 1 course. I hope that you are benefiting from these programs. In the last program, we discussed what is software design and how various design models can be developed from the analysis models. We also outlined the design process and highlighted various characteristics of a good design. We mentioned that there are a number of fundamental design concepts which provide foundation to design correctly, and therefore a designer should be fully aware of them. These concepts are abstraction, stepwise refinement, modularity, software architecture, control hierarchy, structure partitioning, information hiding, and functional independence. Understanding all of these concepts is very important, not to design correctly, but to evaluate the quality of a design. In this program and the next program, we will discuss these concepts in detail. In today's program, we will discuss what do we mean by abstraction, stepwise refinement, modularity, software architecture, and the control hierarchy. So let's start by discussing what we mean by abstraction. Formally, abstraction is defined as a view of problem that extracts the essential information relevant to a particular purpose and ignores the remainder of the information. Two important types of abstractions are data abstraction and procedural abstraction. Understanding the concept of abstraction is very important, and sometimes it is quite confusing. So let's elaborate on what do we really mean by abstraction. The essence of abstraction is to extract essential properties while omitting inessential details of a problem. Abstraction can also be defined as a process whereby we identify the important aspects of a phenomenon and ignore its details. That is, abstraction is the selective examination of certain aspects of a problem. The goal of abstraction is to isolate those aspects that are important for some purpose and suppress those aspects that are unimportant. Therefore, a simplified description or specification of a system that we are going to develop that emphasizes some of the system's details or properties while suppressing other inessential details is the abstraction. A good abstraction is one that emphasizes details that are significant to the reader or to the user and suppresses details that are, at least for the moment, are immaterial or unimportant. One point of confusion regarding abstraction is its use as both a process and an entity. Abstraction as a process denotes the extraction of the essential details about an item or group of items while ignoring the inessential detail. Abstraction as an entity denotes a model, a view, or some other focused representation for an actual item. So you must be very clear about what do we mean the word abstraction when we use it as a process and when the word abstraction is used for an entity. Abstraction as an entity denotes a model, a view, or some other focused representation for an actual item. Abstraction is most often used as a complexity mastering technique. For example, we often hear people saying such thing as, just give me the highlights, or just give me the point, or just tell me the facts. Basically, what we are asking for is that give me the important points, and there is no need of giving the details because we are only interested in the facts and not its details. That means what these people are really asking for is the abstraction. We can have varying degree of abstraction, although these degrees are more commonly referred to as levels. As we move to a higher level of abstraction, we focus on the larger and more important pieces of information using our chosen selection criteria. Another common observation is that as we move to a higher level of abstraction, we tend to concern ourselves with progressively smaller volumes of information and fewer overall items. As we move to a lower level of abstraction, we reveal more detail, typically encounter more individual items, and increase the volume of information with which we must deal. Now, if you remember when we were discussing about DFDs, we started DFD with the context level diagram. That's the highest level of abstraction. And with each level of DFD, basically we are including more and more detail. So the DFDs at the lowest level have more details, and the DFD at the highest level are more abstract in their form. We also note that there are many different types of abstraction. For example, we just said data abstraction and procedural or process abstraction, and even the object abstraction is used. So let's discuss what do we mean by data abstraction and procedural abstraction in little detail. The data abstraction is a named collection of data that describes a data object. As you can see from this diagram, that our object we want to describe is a door. So the object name is door, and we have here a data structure or the information we want to store about that entity. For example, the manufacturer, the model number, type, and so on. The detail is implemented, of course, as a data structure. So by data abstraction, we mean that it's a collection of data items which have been contained inside a container which has a name. Note that data abstraction is provided by almost all the high-level programming languages, such as you might have used records in Pascal and struct in C. All these are the examples of data abstraction, where the fields are hidden inside a record, and the record or the struct has a name. The procedural abstraction, on the other hand, is a named sequence of instructions that has a specific limited function. And you see here another example. Our procedure is open. So this procedure has a name, and of course here we have to put the details or the algorithm that how this procedure will behave or will work. Typically, this is again implemented with the help of some programming language, where we implement the algorithm which specifies that action. If you have some programming experience, you might have noticed that all the modular programming languages like Pascal and C and C++ and other similar languages provide the programmers with procedure abstractions. For example, in Pascal you have procedures and functions. In the case of C, you have functions only. So the function, procedure, basically they are the mechanism which provides you with the procedural abstraction. The data abstraction and procedure abstraction help us in developing a program or software step by step. The process which is commonly known as stepwise refinement. In each step, one or several instructions of a given program are decomposed into more detailed instruction. This successive decomposition or refinement of specification terminates when all instructions are expressed in terms of an underlying computer or programming language, and must therefore be guided by the facilities available on that computer or language. Again, you can compare the stepwise refinement with the way we develop our data flow diagrams, where we refine our data flow diagrams gradually, step by step, level by level. At each level, we put more and more details until we get the process which can be implemented in a given programming language. So let's explain stepwise refinement with the help of an example. Let's say the procedure is open, that's open a door. At the first level of abstraction, we can write it, for example, if you want to open a door, then these are the actions which should be taken. Walk to the door, reach for the knob of the door, open the door, walk through, and then close the door. Then open door. This can be again refined into more detailed steps. For example, open door can be refined into this procedure which says repeat until door opens, turn knob clockwise. If knob doesn't turn, then take the key out. Most probably you are using the wrong key, so you should find the correct key. Then insert the next key into the lock, and then you keep repeating this procedure until you open the door. Once the door is open, then of course you can walk through the door and close the door. Following the similar approach, if you think that some of the steps which are defined at the second level should be further elaborated, then they can be refined further in the next level. So the stepwise refinement is a very, very important phenomenon, a very important technique in developing the programs. Another important design concept is the concept of a module. Let's first define what do we mean by a module. A module is a piece of code or a compilation unit including related declarations and interfaces stored together as one named unit. So module basically is a unit of program which you can save as an independent program, you can compile it, and you might use it whenever you need that one. A module may be a function, it may be a procedure written in a programming language, or it may be a collection of functions and procedures which work together to provide a specific functionality. In the case of object-oriented programming, it might be a class, are a collection of classes which provide some specific functionality to the user. It is important to understand the difference between a module and a subsystem. A subsystem is a system at its own right, whose operation does not depend on the services provided by other subsystems. Subsystems are composed of modules and have well-defined interfaces, which are used for communication with other subsystems. Also, a module is normally a system component that provides one or more specific services to other modules. It makes use of the services provided by other modules. It is normally considered not to be an independent system, as a subsystem could be. Modules may be composed of a number of other simpler system components. This will become clearer to you when we discuss software architecture design in more detail. When a software is composed of a number of modules, it is called a modular software, a very important concept in software engineering. Formally, modularity is defined as, modularity is the property of computer programs that measures the extent to which they have been composed out of separate parts called modules. So basically, modularity simply means that once you develop the software, have you divided your software into modules which are then combined together or integrated together to provide the overall functionality. Formally, modularity is a key design goal of designing and developing any system. So here is one example from our daily life. We have a sound system which composed of various modules. We have separate speakers. Of course, important thing here to note is that all these components, the speaker and the power supply and the cassette player, all these components, of course, can be integrated into a single box, making it a single module. But you see here that these modules have been designed and built separately, and therefore they can be connected to work together. So what benefit we get from here? Of course, each module can be built much easier. If tomorrow you want to change one of the module here, for example, if you want to change the speakers, you don't have to change the whole system. You just have to go buy a new speaker and just connect it to your old system. So it's easy to make the changes into the individual components, and then they can be integrated back into the system. And of course, they are easier to fix. When there is a problem with one of the component, we don't have to open up the whole thing. The only thing is that we have to take out that component which has the problem and fix the problem. So fixing the problem is much easier here because you can easily localize the fault. So modular design, in a similar way, modular design in software engineering provides you all these benefits. A modular design is much more easy to design, it's easier to maintain, it's easier to use. So in the context of software engineering, programs that have many direct interrelationships between any two random parts of the program code are less modular than programs where those relationships occur mainly at the well-defined interfaces between modules. Note that modularity leads to divide and conquer strategy. That is, it is easier to solve a complex problem when you break it into manageable smaller components. So modular programming techniques are those which really increase the modularity. The first and most important quality of modular code is encapsulation. Well-encapsulated module does not expose their internals, that means the logic or the program code, to each other. They don't call into the middle of each other. I have seen many people writing the program in the programming language like Fortran, and they jump or they go to from one part of the program into another part of the program. And that is not a good example of doing a good modular program. So when one module interacts with another module, that interaction takes place through a well-defined interface, what we call the calls. You make a call, you pass the proper parameters, and that module or function will return you the result. So therefore, the modules communicate using application programming interfaces, what we call the APIs, which are narrow, well-defined interfaces, or set of procedure calls and data structures. This is what the rule of modularity is about, that you should create the modules and provide the APIs, and whoever wants to use your module, he should simply use that API and can invoke the other module. The APIs between modules have a dual role. On the implementation level, they function as choke points between the modules, preventing the internals of each from leaking into the neighbors. On the design level, it is the APIs and not the bits of implementation between them that really defines software architecture. One good test for whether an API is well designed is this one. If you try to write the description of it in a purely human language with no source code extract allowed, does it make sense to you? If it makes sense to you, then of course it's a well-defined API. So it is a very good idea to get into the habit of writing informal description of your APIs before you code them. Indeed, some of the most able developers start by defining their interfaces, writing brief comments to describe them, and then writing the code. Since the process of writing the comments clarifies what the code must do, such description helps you organize your thoughts. They make useful module comments, and eventually you might want to turn them into a roadmap document for future readers of the code. As you push module decomposition harder, the pieces get smaller and smaller, and the definition of APIs get more important. Global complexity and the consequent vulnerability of bugs decreases. Dear students, when software is composed of a number of modules, it is important to specify how these components and modules are to be organized, how these modules will interact with each other. Control hierarchy, also called the program structure, represents the organization of program components or modules and implies a hierarchical structure of control. Different notations are used to represent control hierarchy, but the most common is the tree-like diagram that shows hierarchical control for call and return architecture, as shown in this diagram. Here, on the top level, we have the man controller. Then we have module A, module B, and module C just under the module manager or the man manager. Then the module A makes the call or interacts with module D and module E, and module D then in turn interacts with module F and module G, and so on. If you compare this diagram with the program you might have already written, consisting of different functions, then you can think like that the manager is just like your main program. The main program makes a call to your function A, function B, and function C. Then function A, in turn, makes call to function D and function E. And function D then makes the calls to function F, and so on. So this is the way generally we organize our program as well. So you can see one more important thing here. The software component has been organized in the hierarchical structure. That means the software has been divided into horizontal and vertical components. The components which are on the higher level of the tree, basically they are the control components. They generally don't do too much work by themselves. They only make the calls to the lower level components. And the module or the components which are at the lowest level, they are basically the work module. They implement real logic of your program and provide these services to the higher level modules. Dear students, when designing modules, it is important to design modules in such a way that information, that's procedure and data contained within a module is inaccessible to other modules that have no need for such information. This is what we call information hiding. Information hiding improves software maintainability and reduces error propagation. It is important to note that encapsulation is not the same thing as information hiding, as is generally believed. Dear students, in today's program we discussed what is abstraction. We discussed how we develop the programs or a system using a stepwise refinement technique. We discussed what we mean by modularity and why it is important to design a modular system. We also discussed what we mean by software architecture. We discussed the control hierarchy, basically which defines that how the modules are organized and how they interact with each other. We will continue our discussion on the design concepts in the next program as well. Till then, Allah Hafiz.